this is like pure water will dissociate into H plus and OH minus. Or this is a simplified version. What it actually does is two H2Os, instead of H plus, it's really H3O plus and OH minus. But for the purposes of AP Chem, it's fine to write H plus. Like, they don't ding you for the FRQs for that. So that determines pH. Yes, I just started recording. Okay. And so this is called the K for that reaction, or that dissociation, 1 times 10 to the minus 14, is called KW. That's sometimes called the water dissociation constant, or the water constant.
Wait, is K like the thing where you do the products over reactants?
Right. It's the K from the unit 7, the products over reactants. Right. So that would be the concentration of H plus just to the first power times the concentration of hydroxide also to the first power, and not over the concentration of H2O because that's a pure liquid and we leave the pure liquids out of that expression. Okay. So that's water. That's like the basis of acids and bases. The definition for an acid is a proton donor. Proton, in other words, H plus donor, something that gives a proton to something else in a reaction. And a base is a proton acceptor, something that will take the H plus and make it part of its family. So anything that donates a proton is acting like an acid, and anything that accepts a proton is acting as a base. There are other definitions of acid and base, but this is the one that counts in AP Chem. It might be helpful to write the strong acids. There are 6 of them, which are worth memorizing if you have time. HCl, HBr, HI, so hydrochloric, hydrobromic, hydroiodic, and then HClO4, so the perchloric acid with the perchlorate ion, H2SO4, which is sulfuric acid, and then HNO3, which is nitric acid. Probably the most common ones you're going to see are hydrochloric, sulfuric, and nitric. And then there's also strong bases. Let me list some of those. Lithium hydroxide. All the strong bases are stuff that will dissociate and make hydroxide. So the column 1 alkali metals with hydroxide make a strong base. Sodium hydroxide is probably the most common example. Potassium hydroxide or rubidium hydroxide. So that's all the group 1 stuff. And then also group 2 stuff, so like calcium needs 2 hydroxides because the calcium ion is a +2 charge. Strontium, barium. Basically, stuff from groups 1 and 2 paired up with an OH makes a strong base. And strong, we go to the bottom board. Strong means they fully dissociate in water. Like the KSP for the dissociation, or Ka really, the acid dissociation constant. Like these, they go to completion, those reactions. So for example, HCl, if it's aqueous, if you add liquid water, then you will get H3O plus. The acid donates its proton, aqueous, and you will get Cl minus, aqueous. I shouldn't write that as an equilibrium because since it's a strong acid, that will go to completion. All of these particles will split into these. That's what makes it a strong acid. And a strong base, similarly, NaOH, for example, aqueous, would go to completion and dissociate into the sodium ion, aqueous, and then all your hydroxides would become aqueous. And so this part makes the strong acid an acid, this part makes the strong base a base. In solution, we would say these go to completion. So that means if you're doing stoic, for example, and they tell you a concentration of a strong acid or base, like if you have 2 molar NaOH, you can just say, oh, I'm going to have a 2 molar concentration of hydroxide. All of this turns into that. Or if you have 1 molar hydrochloric acid, you have a 1 molar is the concentration of H+, which makes your pH calculations easy. Also, let me just label here, maybe I'll do this in blue, the conjugate pairs. So HCl is the acid in this top reaction. The conjugate base to HCl, conjugate pairs are different by 1 proton. So the acid donates its 1 proton, and so the conjugate base to that is the chloride ion, conjugate base. And then the water is accepting the proton, so it's acting as a base, and then H3O plus is the conjugate acid to that base. And since this is a strong acid, its conjugate base is weak. And then, so this would be your base. And, well, that one's harder to assign because it's not different by protons, so don't worry about that. Okay, that's easy. Enough. Fully dissociates.
Wait, so a strong acid is a weak conjugate base?
A strong acid, a stronger the acid, the weaker the conjugate base. The stronger the base, the weaker the conjugate acid. Because if it's a strong acid, that means it wants to donate all of its protons. So really, it's a more stable state in this configuration. Mm-hmm. So the base, Cl acting as a base, means it's going to accept a proton. If this is good at breaking apart, then this is bad at clumping back together, because the broken apart dissociated version is more stable. That's the preferred side. Okay, weak acids, you have to actually, they don't fully dissociate, so you have to worry about what the dissociation constant is. So here's an example. Ammonia, NH3, if that is aqueous and H2O liquid, you will get an equilibrium. That's your NH4 plus and OH minus. Those would both be aqueous. Aqueous. All 4 of those species are present in solution because it's weak, so it's an equilibrium. Which means the concentration of, for example, OH minus, like to find the POH, you would need to figure out what is the K for that reaction and do a calculation. It's not as easy as all of it reacts. I was not going to do an example quite yet. Let me talk about pH first. Let me go back to the top board, actually. pH pH is defined as the negative log base 10 of the concentration of H plus in your solution, or negative log of the concentration of H3O plus, if you think about it that way. Either way is fine. You're going to get the same number. So this depends on two things. One, the strength of the acid, like what percent of it actually ionizes to make H plus, and the concentration, like how many moles per liter of acid. And then within that acid, how much of it actually dissociates into H plus. And likewise, POH is the negative log of the concentration of OH minus hydroxide. In general, in this unit, the lowercase p means take the negative log base 10 of whatever the p is in front of. So for example, for water, which I just erased, the pKw of the water constant is the negative log of Kw, which was 1 times 10 to the minus 14. So that equals 14. You take the power of 10, flip the negative sign, so it's positive. The pKw is 14. Again, at 25 degrees C. It's going to be different at different temperatures. But for water, what that means is the concentration of H plus and the concentration of hydroxide are equal to each other, which means it's neutral. It's a neutral solution. And from the previous equation, this, remember, is just the product of these two concentrations. And if they're equal, then the concentration is just the square root of this. So it's 1 times 10 to the minus 7 moles per liter. And that tells you that if you slap a P on there, pH and POH are the P of this, which is positive 7 for water. But that's still, it's only when it's at 25 degrees Celsius. Other times, the water constant is different, and so the pH is different, even for pure water. So being neutral is more about this being true than it is about having a pH of 7. Okay. So here's an example of a pH with actual numbers. Example, say you have NaOH and you have the concentration of 0.01 moles per liter, NaOH. Okay, and you want to know what the pH is of that solution. That's going to dissociate like this. NaOH is going to fully dissociate because it's a strong base. So if I have 0.01 moles per liter of NaOH, that means I'm going to have 0.01 moles per liter of hydroxide. They're all going to dissociate. That makes it easy. So it's easier, first of all, to figure out from that what's the pOH of my solution. The negative log of the concentration of hydroxide. So negative log of this, 0.01 moles per liter, which is the same as saying 10 to the minus 2, right? So the log is 2. The negative log is positive 2. The pOH is 2. And if I know that the pH PAH and the POH have to add to 14, then I can just subtract my POH from 14. So the pH then has to be 12 in that case. Maybe I'll put a side note here. pH greater than 7 means you have a base in excess. pH less than 7 means you have an acid in excess. Again, at 25 degrees C. So in general, higher pH is more basic. Cool. I didn't draw any ice tables in the equilibrium notes, so I think I should probably do that now. Just as a generic example, oops, let's talk about a weak acid equilibrium. For example, I just had a good one. Oh, okay, yeah. So I'll do a generic acid here. HA is going to be my acid plus H2O, H3O plus A minus aqueous. So this is my just generic weak acid. This is the conjugate base. Initial change equilibrium. Remember this? The ice box or ice table. Okay. So I'm just going to do some generic, like with symbols here. Say the initial concentration of the acid is, let's call it capital Y.
That's lowercase.
Are you punking me?
I didn't say anything.
That's
I
lowercase.
didn't say anything.
Um,
Look at her.
The pure liquids you can ignore. So in these charts, doesn't really matter. I feel like it would be more curved would be lowercase since it's straight, it's capital. Okay, so you're starting with 0 of the dissociation products. That's always going to be true unless you have some other common ion stuff going on. Change, let's say it's minus X, right? It'll go down, so at equilibrium, you will have Y minus X as the equilibrium concentration of the weak acid. And if my stoichiometric coefficients are all 1 in this example, then if the concentration of HA went down by X, then the concentration of my H3O plus went up by X. So did my concentration of A minus, the conjugate base. And so my equilibrium concentration is X and X. Like that. So generally, this number X for a weak acid is going to be small compared to Y. So if you want to find the Ka, the acid dissociation constant, you would do, well, in this example, your concentration of H3O plus, concentration of A minus to the first power over the concentration of HA, which at equilibrium we have representations for. So this would be X squared on the top, X times X, and then over Y minus X. So that can get ugly. Sometimes they'll give you Ka and ask you what X is, and don't spend a lot of time on that. The trick is, if X is a lot smaller than Y, then you can just approximate the Y minus X as being equal to Y. And then it's a lot easier to solve for X, because you would be given the initial concentration Y, and the Ka, and you could solve.
So with all weak acids, we should just ignore the X on the bottom?
I would say if you find yourself stuck in some gnarly quadratic math, they don't want you to go through all of that. They want you to make that estimation that y minus x is approximately x. Okay. And similar for a weak base. Okay. How much time do I have?
We have like 9 minutes.
9 minutes. That's okay. We'll talk about titration, I guess, real quick. And titration curves. Maybe they don't like me. Maybe they just want to.
I'm gonna say maybe they don't like you.
Maybe they just want to forget all of the AP Chem because it traumatized them, and they're just hoping that by sheer luck they'll ace the exam.
Most of them aren't even taking it.
Well, I only invited the people who signed up according to the list they gave me.
Yeah, they
Oh, by the
probably-
way, they gave me a schedule today of AP exams.
Ours is April 1st at 12.
May 1st at 12. Yes. Where did I put that? I'll email it out. They told me like where on campus it's supposed to be and when you're supposed to show up. So I don't remember. I think it was in a classroom though, not the library.
I liked mine in the makerspace in the library. I did that for Prop PC. That was nice. There are also just like not many of us. I didn't take mine.
I did mine in the gym, and there was a glare on the clock, so I had no idea how much time I had left. It was not fun.
Oh, that's not good.
Felt like it.
Okay. Let's just talk about titration curves. You will see some of these. This is where you have, for example, the pH is always plotted on the y-axis of a curve like this. And then, let's say as this example, you are adding 0.1 molar HCl and you're adding 0.1 molar NaOH. Okay, so this is going to be the volume of the NaOH that you add. So yeah, this is a strong base and a strong acid. You're adding the base to the acid, and you'll get a curve that looks something like this. You'll have a low pH to start because you're starting with just acid. As you add base, it will slowly increase the pH, and then it will go up very sharply. And at that point right there, that's called the equivalence point. The equivalence point is where you have exactly stoichiometrically matched the amount of H plus and OH minus. The number of particles is equal, so it's perfectly neutralized. Every one H plus has been neutralized by one OH minus. Okay. Sometimes you might see a curve that has more than one step, like that. And that would be for, say you were doing the same thing, adding NaOH, but that would be for NaOH added to like H2SO4, where at this point, the H2SO4 is an acid that's going to donate 2 protons. One of them will come off more easily than the other one. So at this point, all of the first protons in the H2 have been neutralized. And then at that point, the second bunch of protons have been neutralized by the NaOH. And after that, you're just adding excess NaOH, so you get high pH. Okay. if you have a weak acid, maybe I can just erase this. Lost track of what I was going to say. Polyprotic acid.
When the trees are.
I'll just do I'll do the Henderson-Hasselbalch real quick. I think that'll be good. Or the HH equation. Oh, here, wait, I know what I was going to say. A weak acid plus NaOH. Okay, so same curve here, pH, NaOH, volume added. You get something like this. Here's your equivalence point. Halfway to the equivalence point, on this axis, half equivalence point is relevant for a weak acid because the pH of the weak acid equals the pKa at the half equivalence point. That's a question they like to ask about. Equivalence point. So they might give you a graph like this for a weak acid and say, what's the Ka or the pKa? So you would look here at the half equivalence point, you would read from the graph what the pH is, and that's the pKa. And then from there you could get the Ka.
Only for a weak acid.
For a weak acid, yeah. For a strong acid, the Ka is enormous. It's so big that it's not really measurable. At least not easily. So you don't really talk about the Ka unless you're talking about a weak acid. Okay. So buffers, the last bit. Buffers, pH, and the Henderson-Hasselbalch equation. Let me just write it up here. This is on your equation sheet. pH equals the pKa plus the log
have 3 minutes left.
concentration of the base
Wait,
over
what time
the
is class
acid.
then?
This is one.
Let me look at this. The bell rings at 12:21 today. So that's again for this reaction, an acid dissociating into H plus and A minus.
So then it's lunchtime now.
Yeah, it is, yeah. Third period is going to start after this.
Wait, not lunchtime? So,
No, it is lunch.
okay. So what happens before period 3? So
There's
is
passing
this-
period.
Is this lunchtime?
Yes.
Yes.
What
Yes.
the
All right, just to add a little more about buffers, because that was a little rushed. Buffer is a solution that resists pH change when you add small amounts of acid or base to it. And it does that because it contains in a buffer solution a weak acid and its conjugate base. So, for example, if you have this reaction of a generic weak acid, where this would be the weak acid, HA, and this would be the conjugate base. If this is a weak acid, that's going to be an equilibrium, and your system is going to contain a bunch of particles of HA in solution and a bunch of particles of the conjugate base, A minus, in solution. So that is your buffer system. And then if you come add more acid into this system, the conjugate base in the solution is going to absorb the protons from that acid. It sort of mops up the acid that you add to keep the pH pretty stable. If you come along and you add base into this system when it's at equilibrium, then the weak acid can donate protons to neutralize the base that you add. So the weak acid in solution can mop up any base that you add, and the conjugate base in solution can mop up any acid you add. As long as you're adding small amounts. At some point, you're going to overwhelm the system, and the pH will shift more significantly if you add large amounts of acid or base. But for small amounts, a buffer will resist changes in pH. And so for a buffer, the pH is given by the Henderson-Hasselbalch equation. pH equals the pKa plus the log of this ratio, the base over the acid concentrations in solution. And so that explains why we said at the half equivalence point on a titration curve, the pH equals the pKa without this. Because at the half equivalence point, this term equals 0. So maybe I'll write that over here. At the half equivalence point, what that means is half of the acid has been neutralized. And so, or half of it, it's halfway to being fully gone. So you have half of it as the acid and half of it as the conjugate base. Those concentrations are the same at the half equivalence point, which means this ratio of the base over the acid, if they're equal, the ratio of them equals 1, and the log of 1 is 0. So at the half equivalence point, this term is 0, and the pH equals the pKa. Otherwise, if you're not at the half equivalence point, you have to know the concentrations, or you could figure out the ratio, and mostly the problems are just manipulating this equation to solve for an unknown. Last thing with regards to that, the pH, if it is greater than the pKa of the weak acid, then this term has to be positive, which means that the concentration of the base has to be greater than the concentration of the weak acid in the buffer. Okay, and you could figure that out just from looking at this equation. If this number has to be bigger, this part has to be positive, which means we need the log of something greater than 1, so the top of that fraction has to be bigger. And then the reverse is also true. If the pH of your solution is less than the pKa, that means you have more acid. So the concentration of HA, the weak acid, is more than the concentration of the conjugate base. If they're equal, if the concentrations are equal, then you're at the half equivalence point, and the pH is exactly equal to the pKa.